Hello everyone, welcome back. For the last 3 classes, we have been discussing about what are the applications of CFD, what are the domains where CFD can be used, and we saw that it is used almost everywhere in our life, wherever the fluid is involved, wherever we want to arrive at a new design or even want to characterize an existing design. The CFD is a very good tool. It is very easy to use and it has certain advantages over the experimental processes, but I mean we need to remember that for any CFD to work, we need to basically validate it with the experimental data and then you will get the correct result. Okay. And we also saw what are the things we need for CFD, the pre-processing, the grid generation, then server setup and finally the post-processing. So, what you see in a good paper, some nice diagrams like you are seeing here. Okay, for example, on my front slide, okay, this diagram that you see, this is after going through all the processes, and then you try to basically look at the features in the flow, right? And then it can be qualitative also and quantitative also. Qualitative means you want to see the contours, streamlines, how the flow is behaving in different regions. And quantitative is, for example, you want to see the distribution of pressure at a given line, okay, or maybe the CL and CD. So, all those things are basically quantitative. So, we need to basically match both the qualitative and the quantitative results, okay, before we are good to go for a new geometry or new flow. Okay. So, today we are going to discuss about the CFD frameworks. Okay. So, what do you mean by CFD framework? So, many of you might have used softwares for CFD, for example, the Fluent or maybe OpenFOAM, okay, and there are so many packages that you have. Okay, you have CFD++, okay, you have CFX, okay, and then there are packages by Altair. Okay, so all the packages that you see, they follow a certain way to solve the governing equations, okay, certain way to discretize the grid and then use your schemes and solve it. Okay, I am not getting into whether it is the compressible or incompressible or basically the pressure based or density based. Of course, we will go into that also in greater detail. Okay, but from the way we basically distribute the points and the way we solve, there are certain differences. Okay, so that is what we want to highlight. So, this is just to give you a flavor of what are the different frameworks which are available in CFD. So, here are some of the examples. Okay, so most of the tools that you see in CFD, the commercial tools are basically in finite volume. Okay, and most of the research tools that you see which is used for let us say LES or DNS kind of studies, you would see that many of them are in finite difference. Okay. So, these are the two most popular tools in most popular frameworks in the engineering CFD, and it is very important to understand the difference between the two. Okay, first go with the finite difference. This is very easy to basically represent your differential equation in terms of your finite differential scheme. Okay, so that is the easiest approach. So, if I can give you just a very small example, okay, let us take an example of linear convection. Okay, it is like a wave equation which you might have studied in your math course. Okay. So, there is a convection equation, okay, then the diffusion equation. So, that is for example, heat equation. Okay, when you write a heat equation, you can have unsteady heat equation or steady state heat equation. So, there are different properties. For example, if it is a steady state, it is like an elliptic solver. If it is unsteady, then it is like a parabolic solver. So, these elliptic, parabolic, hyperbolic will come into that later, but right now just try to solve a very simple equation, del u by del t plus c del u by del x equal to 0. Okay, typically any equation that you see will have terms like a term which depends on time, okay, we call it the temporal, okay, this time dependent term, okay, this is basically represents the rate of change, and then you will have something which depends on the flux, okay, or the convection, or a better term is advection, okay. So, how certain quantities are getting advected and getting advected at what speed. In this case, the quantity u is getting advected at a speed of c, okay, which may be the speed of sound. Okay. If you just instead of this, if you write this del u by del t plus u del u by del x equal to 0, okay, this becomes a non-linear problem. This is a non-linear advection equation. Okay. Why it is non-linear? Because here the quantity u is getting transported at the speed of u, okay, which is unknown. Okay. So, here c can be a constant value, you specify in the beginning, and at that it is getting advected. Here the advection speed also has to be determined through your process, okay, through your CFD simulation. Okay. So, if you want to solve this, so if you go to very basic way of discretizing your differential equation, okay. So, like we discussed earlier also, if you recall, we had this is x and this was f x, and we said that we can discretize it like this. Okay. So, this is my delta x, this is my delta f. So, df by dx would become limit delta x tends to 0 delta f by delta x, right. So, similar thing if you use here, okay, and this can be written as let us say f 2 minus f 1 by delta x, right. So, if you write it here, that will be, let us say, if I write time on top, so this is u n plus 1 minus u n by delta t, and let us say I am trying to solve this on a line here. Okay. So, as we discussed in the CFD process, you need to discretize it. Okay. So, let us say this is I equal to 1 to I equal to 20. So, for example, this may be your I, this is I plus 1, this is I minus 1, right, and this is your space, and this side may be your time. So, this is n, so this will become n plus 1, right. So, you are going from n to n plus 1 to n plus 2 and so on and so forth. If it is starting a fresh simulation, then n may be 0, then 1 and 2 and 3 and 4 and up to the time that you want to go. Right. So, that is what at a given point and time like this, you can write it u I n plus 1 minus u I n by delta t plus c. Now, this is a derivative in x, right. So, for the old time that is present here, u n minus u I n by delta x equal to 0. So, what I did here, I represented this del u by del t in terms of this very simple minded approximation which is obtained through the Taylor series, okay. And we will look into more details of what kind of approximation you can have for a continuous function using a discretization approach, and for this we have this, right, I plus 1 minus I by delta x is equal to your del u by del x. So, if you solve it using this approach, make a very nice grid which is where you know what is I plus 1, I plus 2, I plus I minus 2 and so on and so forth, then you can easily solve this problem using this approach, and this approach is called the finite difference approach. Okay. So, those who are starting this for the first time, doing CFD for the first time, the finite difference approach you may find most intuitive, and you can start solving very simple problems like heat equation and so on and so forth. Okay. If it were in 2D, so then you will have a 2D grid. Okay. So, let me erase this. If it is a 2D problem, then make a 2D grid, set up the boundary conditions. So, your 2D grid may be like this. Okay. So, this may go I equal to 1 to 2, 3, 4, 5, 6, 7, okay, and this is j equal to 1, 2, 3, 4, 5, 6, 7, right. So, you can write your derivatives in x, derivative in y and derivative in time, right, in the numerical discretization, and then you see how it is progressing, right. So, I just give you example of linear convection equation, but it can be a very complex equation also, it can be a nonlinear equation, it can be a Navier-Stokes equation, but this is the way you discretize, and only the complexity of the solution will increase, but otherwise the approach remains the same, that you have to discretize your grid, okay, in a manner that you know what is I minus 1 and I plus 1 and j minus 1 and j plus 1, get the derivative, calculate the derivative and solve it. Okay. You can use any time scheme that you want. So, this is something like this is called the forward Euler, okay, but you can have the backward Euler, you can have the Runge-Kutta multi-step schemes, so on and so forth. Similarly, this is called your upwind scheme. Okay. Basically, this is, and then you can have backward also. Okay. So, this is forward difference, right. So, this is how you can solve using a finite difference approach, and you can write a very nice little code in MATLAB also. Let us say if we talk about the problem that we have been discussing, okay, that the lead driven cavity. Okay. So, let us think about that problem. So, your governing equation would be the physical equation that you have, maybe the Navier-Stokes equations, okay, and we will look at the different forms of Navier-Stokes equations later, okay, and you discretize, you calculate the derivative in each direction, put the boundary conditions. So, what are the boundary conditions? So, in 3 sides we have got wall, okay. So, basically all the velocities go to 0 here, and for the top one you have the moving lead, okay, and you solve it. Now, let us say I tell you that okay, my cavity is not like this, but let us say I have a triangular cavity. Okay. So, let us say I have a cavity which is like this, okay, or even more complicated, right. Here this lead is moving. Okay. Then if you try to make a finite difference grid like this, you will have problem, okay, because at this point this corner you will have the singularity, right. So, if you want to solve the same problem, basically the governing equations are the same, the Navier-Stokes equations, okay, and then you have a lead moving, okay, but if you want to solve this using a very nice grid like we have done for this square cavity, it will be very difficult, right. So, what you can do rather is basically you can create a grid which is maybe something like this, you can fill in elements the way you want, okay. You might want to ensure that there is a boundary layer close to the wall, okay, that we are able to capture the velocities, the boundary layer properties well, okay. Let us say you made a grid like this. Now, in this you cannot find, if I say that give me, so this is let us say some ij, okay, and if I ask that give me the j plus 1 and I plus 1, okay, and I minus 1 and j minus 1 and so on and so forth, right. So, what is your j plus 1, right. Even if you can give the j plus 1, I may ask you what is give me j plus 2, j plus 3, j plus 4 and so on and so forth. It is very difficult to define because this grid is unstructured, in the sense that there is no proper structure present there. All you know that okay, I have got this cell, okay, let us say this is a cell, and for every cell edge face I have got the left cell and right cell, okay. This is left cell and right cell, left cell and right cell, left cell and right cell, right, and this is true for every cell. You can find out, you can take this cell here also, you have this here, both the sides, both the sides, both the sides and so on and so forth, right. So, for every edge, okay, where the flux may be going, you know what is the left cell, what is the right cell, and this is my edge of the cell, right. So, in this case we solve an integral form of the Navier-Stokes equations instead of doing this del of, like you are doing del u by del t plus c del u by del x equal to 0. Okay. Earlier what we will do, we will have this integral form, okay, and we will in the case of 1D you can do it for this entire delta x, okay, maybe which is the, this is one cell here, okay, this is maybe delta x, and solve the integral form. Okay. You will apply the Gauss divergence theorem to convert your volume into surface and so on and so forth, right. And all you require in this particular problem is the what is my left cell and right cell, and from that information you can calculate your derivative, okay, or the gradient. Of course, you can have more information, for example, how many cells are connected through this corner or through this corner or through this corner, right. Then your from the neighbor you can calculate the gradient little bit better, or you can have the phase sharing neighbor or edge sharing neighbor and the vertex sharing neighbor. So, if you use this approach where you are using an integral form of the Navier-Stokes equations, okay, and you ensure that the convergence of mass, momentum, energy, etc., is done in every single cell. Okay. So, in this approach is called the finite volume approach. This is finite difference and finite volume, right. So, what are the advantages and disadvantages of the finite difference and finite volume? The advantage of finite difference is that because you have the information about the stencil, complete information from I equal to 1 to I equal to 100, I can ask you, I can give you any point, let us say I give you I equal to 10, you can give me I 9, 8, 7, 6, 5, 4, 3, 2, 1, and similarly on the right side 11, 12, 13, 14, 15, 16, 17, right. So, you have stencil information, you have stencil information available everywhere. So, you can go to very high order schemes, okay, as we will see later that, right, if you are just calculating this du by dx, okay, using only the left and right point, let us say ui plus 1 minus ui by delta x, you have certain accuracy, okay. But if you can involve, let us say I minus 1, I plus 1, I plus 2 and so on and so forth. So, and you can have I minus 2 also here, okay. So, if you use more number of points to calculate the gradient, the accuracy will be better, right. So, the finite difference you can use high order schemes, right, because you have the stencil information and you can increase the size of the stencil and you can approximate your gradients better, right. So, that is the advantage of finite difference, but what is the disadvantage? If you have a very complicated geometry, okay, then you cannot use finite difference because you cannot make a nice structured grid on that. Okay. One very good example is, let us say you have an aerofoil which has got a slat and a flap, okay, and you make a domain around this, okay, and there is a gap between the slat and the body. So, you will have grid points here also, okay, if I can make it grid points, grid, okay, you have grid cells here also and here also, and you have no slip boundary condition on the surface. So, you cannot make a structured grid on this kind of problem, okay. If you want to simulate an entire aircraft, right. So, it's very difficult to make a structured grid even if you use multi block and so on and so forth, right. So, in those cases the option that you have, a good option that you have is finite volume. So, that is the advantage of finite volume, it can take any kind of geometry, okay, and you can create, you can put it with hex cell. So, there are hexahedral cells, okay, you will have tetrahedral cells, okay, then you have prisms, okay, and in the 2D you can have quad, okay, basically the quadrilateral, triangle and so on and so forth, okay. So, very close to the wall, if you want to capture the boundary layer. So, in a 3D flow you want to put a prism layer on top of that, so that the grid is aligned to the body very close to the wall, right. So, what I mean by that is basically you might want to make some layers of grid here, okay, maybe 2-3 layers like this, okay, where you are capturing the boundary layer, and after that you can start filling the elements like this. Okay. Similarly, you can do for the slat and so on and so forth. So, what you did, you captured your boundary layer using the prism kind of cells, and then away from the body you can put whatever kind of shell that you want, right, and this you can fill in everywhere in the domain. Okay. It does not matter what kind of shell you want, because your gradients are calculated using your left shell and right shell, okay, and maybe your phase sharing neighbors or node sharing neighbors and so on and so forth. Okay. So, the disadvantage of the finite volume approach is you cannot basically get very high order accuracy in the finite volume, because of the very fact that you do not have information about the stencil, information about the long stencil. Okay. You do not know what is I minus 3, I minus 2, I plus 2, I plus 3 and so on and so forth. So, you cannot use a the finite difference formula which is applicable for a long stencil, right. So, you cannot reach very high order accuracy, but you can solve any kind of problem which requires a complicated grid and complicated geometry. Okay. So, in this case, for example, if you look at this grid, lead band cavity, if you want to use finite difference, you can use this grid directly, right. So, finite volume can take structured grid also and unstructured grid also, and the structured grid is more accurate. I mean, solution on a structured grid is more accurate generally than the unstructured grid. Okay. So, here for example, you want to solve this lead band cavity problem, you can use this grid, or may you want to break down here, okay, whatever thing you want, okay, and you can make another grid, because you do not need any information, and if you certain region you want more accuracy, you can break the grid and you can get more accuracy there. Okay. Then there are there are approaches like the finite element. Okay. So, this is more involved, okay, and but it is very accurate. Okay. This started from the structures, okay, but now it is also very popular in your CFD. Some of the research codes use this finite element approach. So, here it is because it is inspired by the structure. So, it is called element here, and then you have accuracy in terms of P and H. Okay. P is basically the polynomial and H is the size of the element, right. So, you can fit a polynomial inside an element. So, that gives you more accuracy in calculating the gradient, and H is basically you can decrease or increase the size of the element. Okay. So, in this course we will mostly cover finite difference and we will have some information about the finite volume. Okay. Then in physics the very popular approach is the spectral and the pseudo spectral. Okay. Why? Because when you are trying to solve a problem which says, let us say some of the convection problem, or let us say homogeneous isotropic turbulence kind of problem, okay, turbulence in a box, where you can make use of the periodic boundary condition, right. So, for example, let me just let us say you want to solve turbulence in a box, right. So, what do you mean by turbulence in a box is basically, okay, this is a box, okay, and you put some disturbance in the beginning, okay, something, it may be your the sinusoidal vortex or anything that you want, and then you put in the Navier-Stokes equation. Because of the non-linearity, the turbulence will develop and you will get more and more structures in the flow, and you might want to analyze what happens when you change the Reynolds number, what happens when you change the grid size and so on and so forth. So, if you just want to analyze this, you do not need to have a boundary layer, there is no wall, nothing. Okay. So, in this case you can utilize for example a periodic boundary condition. So, whatever is getting in is getting out here, here, and then this side and this side, right. So, in this case you can utilize your periodic boundary condition. So, whenever there is a periodic boundary condition, you can use the spectral properties, right. You can basically approximate, you do not have to approximate using a discretization your fx, but your whenever you discretize it, you can basically gradient at each point accurately by if you write it in terms of your Fourier series. Okay. So, that is the advantage spectral, that you can have the periodic boundary conditions. If it is possible, then you can approximate the gradient by not having one stencil, two stencil and so on and so forth, but from boundary to boundary, from one end to another end, every point in your grid will have the gradient exactly defined, okay, by using the Fourier transform. Okay. So, that is the advantage of spectral. Similar thing is pseudo spectral. Okay. So, here some boundaries may be periodic and some boundaries may not be periodic. Okay. And then you have the grid free. So, what is grid free is that you do not have basically the grid, okay, but what you have is point cloud. Okay. So, for example, let us say you are trying to simulate. So, there is an aircraft going, a military aircraft, it is dropping a missile and the missile is going down, and you want to see that what is the trajectory of the missile, and you want to simulate this entire process. So, as the missile is going down, right. So, you have to basically accordingly keep on changing the grid, because it is a dynamic problem. So, every time you have to readjust your grid and solve the problem. But instead of grid, if you can put the point clouds there, okay, so then it becomes easy to solve this problem. Of course, your accuracy may be little lower, but you can easily solve this problem without going to very high computational cost. So, these approaches are called the grid free approach. So, these are the main primary approaches. There are other approaches also. For example, there is something called SPH, okay, smooth particle hydrodynamics, and there are spectral volume, okay, SV. Okay. So, you can go through and read these different frameworks which basically make use of the Navier-Stokes equation and solve problems in using different approaches. Okay. You can also have approach called immersed boundary method, where what you can do is like, let us say you have an aerofoil, go back to the another problem, and then you make a grid, but what you do, you make a grid which is kind of structured grid like this. Okay. So, this is like a body, an aerofoil is immersed in the grid, right. So, if you can figure out what are the points where it is immersed, okay, you can on those points you can probably apply your no slip boundary condition, right. So, this approach is called the immersed boundary method. So, what is the advantage of this? That you can still use your structured way of gridding the domain, but at the boundary you have to use some special boundary conditions. Okay. So, you can go to higher order approach as long as you can maintain the boundary conditions very close to the body. The disadvantage is that if you want to resolve the boundary layer, you would like your mesh to be very aligned to the body, right, which is not possible in this immersed boundary approach. Of course, you can make locally more refined and try to make your gradient calculation more and more accurate, okay, but it is not same as basically putting a boundary layer grid. Then lattice Boltzmann, okay, this is also become very popular for solving fluid flow problem, but there is a fundamental difference between lattice Boltzmann and what all I talked till now. In the lattice Boltzmann, we use the lattice Boltzmann equation instead of Navier-Stokes equation. Okay. You know about the Boltzmann equations, and then you can basically in the limit where your Knudsen number goes to 0, okay, or very small, you can basically use those equations on a lattice to solve problems of fluid mechanics, solve problems which are in continuum. Okay. So, these approaches are called lattice Boltzmann approach. Here you have a lattice, okay, which looks very close to the grid, okay, but these are called lattice points because you want to calculate the speed of sound and many other properties based on using the slot lattice property. Okay. And you can have different kind of lattices, okay, you can have BCC, FCC and so on and so forth, right. You can have the discontinuous Galerkin approach, this is also called the DG approach. Okay. So, this is actually like the finite volume approach, but then you also have the polynomial inside that, so that you can increase the order of accuracy inside every single volume. Okay. You can have vertex panel method, this is basically low order method. You try to basically tell that the vortex distribution, everything is due to the vortex distribution, find the circulation and get the value of the aerodynamic quantity that you want. spectral volume and SPH I already spoke about. These are the emerging methods to solve the fluid flow problems. Okay. So, now that those were basically the approaches, but you can have different formulations also. You can use incompressible formulation or compressible formulation depending on the way you want, depending on your requirement. And remember, there is a great difference between these two formulation. Okay. And we will get into those details in the future lectures. You can use the coupled approach or the segregated approach. When I say coupled approach, that means you are solving for all these quantities at the same time. Okay. So, these are basically or in a simple way you have rho u v w p at the same time, or in other way all the equations are solved simultaneously. In the segregated approach, you can solve one after the another. Okay. You can solve for mass conservation, then momentum, then energy, and so on and so forth. In the coupled, you can solve all three equations together. You can have pressure velocity formulation, or you have kind of vorticity stream function formulation. So, the advantage, so you can write your Navier-Stokes equation in terms of vorticity in stream function, right. So, it has also certain advantage, but the disadvantage is that assigning the boundary condition for vorticity is not that straightforward. Okay, but it has been found very useful for certain problems. You can solve in Cartesian coordinate system or the curvilinear coordinate system. We will have discussions about this curvilinear system in the future. You can have the Lagrangian or the Eulerian framework, okay, where the Lagrangian you actually follow the particle, and in the Eulerian you basically fix a location and see how the particle are traveling. Okay. You can have the variables which are like primitive. So, these are my primitive variables, and this is called the conserved variable. Okay. So, in the incompressible it's more popular to have primitive variable, and in conserved it is more in the compressible it is more popular to have conserved variable, and the reason for that is basically your density is also a varying quantity. So, you basically put the density multiply by the primitive variable as a new variable. Okay, these are called the conserved variables. Okay. Then quickly the grid topology I already talked about, the structured unstructured grids. Okay, you can have blocked structure also, because some, let us say the domain is slightly complicated. You can make a structured grid, but you have to have different kind of structured grid at different locations. So, these are called the block structured grids. You can make different blocks and make a structured grid there, but you can use a finite difference method there. You can have an overset mesh, okay, basically one mesh at below and one mesh above, and they will be an interpolation between the two meshes at every point. You can have like first order, second order kind of interpolations. So, these kind of approaches are also used in complex problems, and point call-outs I already told. Okay. You can have the distribution of points instead of a grid. Okay. In the finite volume, you can have the values of the cell, which is can be cell centered or it can be vertex centered. So, if this is your finite volume, okay. So, you can have this is cell centered. So, you can have the values at the cell, or you can have vertex centered, okay, where the values are stored at the vertex. Okay. Both methods are popular, although cell centered method is more common. Okay. And then in a finite difference you can have collocated or staggered. When it is collocated means all the pressure as well as the velocity quantity are basically defined at the same location. When staggered, your pressure and velocity quantities are basically defined by staggered by basically half cell distance, and there are certain advantages when you use staggered grid, particularly for the incompressible flow problem. Okay. Okay, so with that we will stop here. In the next class we will review some of the aspects of the compressible flows, and then we will go to the governing equations. Thank you very much.